So chapter 5 starts our study of the trigonometric identities. This whole first page is a really nice formula chart for you, and we're going to continue to add to this formula chart essentially throughout this whole chapter. But I went ahead and filled it out for you, so you can just pause the video and fill this entire thing in so you don't have to listen to me talk. But just as an overview, we have all of the reciprocal identities, the quotient identities, and our Pythagorean identities. I've also written down all of the alternative forms of the fundamental identities, so just rearranging this equation so that you have them listed on your formula chart. These will come in handy to recognize variations of these Pythagorean identities. And then we have our even-odd identities, which is the only thing we haven't seen before from this page. And basically it says that if you're taking the sine of a negative angle, it's just the negative version of the regular angle. Same for cosecant. For cosine and secant, the cosine of a negative angle is just the positive cosine of that angle, so it doesn't basically float outside. And for tangent and cotangent of a negative angle, it is just negative tangent and negative cotangent. So again, pause the video here, get all of these identities written down for yourself on this formula chart, and we'll start on the next page with a problem. So we've actually seen questions like example 1 before, way back in like chapter 2 or 3. It says if tangent of theta is equal to negative 5/3 and theta is in quadrant 2, find each function value. So if we're finding the secant of theta, first of all, remember we're in quadrant 2, and in quadrant 2, secant, which is the reciprocal of cosine, will be negative. So just keep that in mind that our answer should be negative at the end. Now, using one of the Pythagorean identities, we have the relationship that secant squared of theta is equal to tangent squared of theta plus 1. I'm choosing to use this identity because it relates secant to tangent. So in this problem, those are two things either we know or we want to know. Well, let's plug some stuff in. We know that tangent of theta, based on the problem, is negative 5/3. So if I have that squared plus 1, that's what would be equal to secant squared of theta. So if we work with just the right side of this equation, negative 5/3 squared is 25/9. And so if I'm adding 1 to that, it's like adding 9/9, which makes this 34/9. Now, of course, that is equal to secant squared of theta. And if I just want secant of theta, I need to take the square root of both sides. I have to remember to put plus or minus since I'm actively taking the square root of this equation. But immediately we remember that since we're in quadrant 2, secant should be negative. So we can take the square root of the top, the numerator, and the square root of the denominator. So we get that the secant of theta is equal to negative square root 34/3. For part B, in quadrant 2, remember sine is positive. So if we have to make a choice later, we'll know that sine should be positive. If we find some relationship between sine and tangent, we just have a typical quotient identity. Tangent of theta is going to be equal to sine of theta over cosine theta. So let's plug in what we know. Again, we know from this problem that tangent is negative 5/3. That's what's going to be equal to sine of theta over cosine theta. Well, I want to isolate sine of theta, so I'm going to multiply both sides by cosine of theta. So that sine of theta is by itself. Okay, cool. The only thing that's really left is for us to fill in some number for cosine of theta. But remember, we found already what secant of theta was equal to. And secant and cosine are reciprocals. So I can substitute in the reciprocal of the value we found in part A, so negative 3 over square root 34. Yes, I know that square root is in the bottom. We'll deal with it in a second. In for cosine. Let's start reducing some stuff. So the negatives will cancel each other out. The 3's will cancel each other out. We end up with 5 over square root 34, which, yes, you will rationalize that denominator so that you end up with sine of theta being equal to 5 times the square root of 34 over 34. And notice that this answer is positive, which we knew from the start should be positive. Part C here says for us to evaluate cotangent of negative theta. Well, in our even and odd functions, we know that there is a identity that says the cotangent of negative theta will just be equal to negative cotangent of theta. It's basically like this minus sign gets to plop on the outside for cotangent and tangent. Okay, well, if we fill in some things we know that cotangent is the reciprocal of tangent. And since our tangent was negative 5/3, we can just use the reciprocal of that value for cotangent. Since negative divided by negative is positive, we then have that the cotangent of negative theta should be equal to positive 3/5. So again, in each of these, we just solved for one of the trig values that we had, just like we've done in other chapters. It's just that we related them from the start, from what I want to know to what I was given, tangent, using a Pythagorean identity, the quotient identity, and an even-odd identity. Now, some of the things we're going to be doing in this chapter is simplifying or proving/verifying different trigonometric expressions. So here's some potential algebra skills that you might need to simplify a trigonometric expression. You might have to combine two fractions with a common denominator. Okay, I'll show you an example of that soon. You may also have to multiply by the trig conjugate of the denominator. As a hint here, a trig conjugate is like 1 plus cosine of theta and 1 minus cosine of theta. So the same thing, just change the sign in the middle of 1 and that value. That is a conjugate. You may also have to factor in various ways. You'll see a lot of greatest common factor factoring and difference of two squares factoring. And of course, much, much more. So in example 2 here, we're going to simplify this trigonometric expression down to just something else. We're going to get it to not have a binomial in the denominator, and then we'll simplify. So we're going to multiply by the conjugate of the denominator. Since this denominator has a plus or minus in it, we want to multiply. So I'm going to take the expression sine of theta over 1 plus cosine of theta, and I'm going to multiply the top and the bottom by the conjugate of the denominator. 1 minus cosine of theta over 1 minus cosine of theta. When I multiply these two things together, the top turns into what looks like a distribution problem. Sine of theta over 1 minus cosine of theta. And the denominator ends up being the difference of two squares. Now this is a shortcut for factoring. It is just simply first, outer, inner, last, first, outer, inner, last. But if you recognize this pattern, it ends up being the first thing squared, which is 1, minus the second thing squared, which is cosine squared of theta. Okay, my spidey senses are tingling here because I noticed that 1 minus cosine of theta is actually one of the alternative forms of the first Pythagorean identity, which means I can rewrite the denominator as simply sine squared of theta. If you don't know what I'm talking about, flip back to the first page and look at those alternative forms of that first Pythagorean identity. We have this written down and it says equals sine squared of theta. I'm able to replace that identity in this fraction. I'm rewriting my numerator. Okay, I can cancel some stuff out. If we notice, sine of theta is going to cancel out one of the sine of thetas in the denominator so that I only end up with 1 minus cosine of theta over sine of theta. Now that this expression is simplified, we can go ahead and split apart this fraction into as if we're getting rid of a common denominator. Meaning I can do 1 over sine of theta minus the cosine of theta over sine of theta. So I split this single denominator, singleton in the denominator, to both the first term and the second term. Using a reciprocal identity, 1 over sine of theta is cosecant of theta, and cosine of theta over sine of theta is cotangent of theta. This is just an alternative or simplified form from where we started. We used a complex or a trig conjugate. We canceled some stuff out after doing the Pythagorean identity. We split this fraction into two and then used two basic or fundamental identities. In example 3, we're going to simplify this by finding a common denominator. Now I'm going to show a lot of work on this problem, And you might be able to skip a few of these steps when you're actually doing it yourself, but again, I want to show you the most on your notes so you understand what's happening here. As with all fractions, you can't add them together until they have a common denominator. So the common denominator I'm looking for is for the fraction to have both 1 minus sine of theta times 1 plus sine of theta. So again, I'm going to show a lot of work, and this is probably the only time I'll show this amount of work. But I'm going to take this first fraction, and I'm going to multiply it by the denominator that it's missing, which is 1 plus sine of theta. And then I'm going to take that second fraction, 1 plus sine of theta, and I'm going to multiply it by the denominator it's missing, which is 1 minus sine of theta. This is the step I'm probably never going to show again. But this allows me to then make one giant fraction with the denominator of 1 minus sine of theta, 1 plus sine of theta. Since now both fractions, the first fraction and the second fraction, have the same denominator. But of course, I have to add those two things on the top. 1 times 1 plus sine of theta is 1 plus sine of theta. And then I'm going to add 1 times 1 minus sine of theta to make this. Again, that's finding a common denominator. This is the only way you can combine two fractions when we're trying to simplify trigonometric expressions. Now what I notice right away is I have positive sine of theta and negative sine of theta on top. They're going to cancel. I also notice that then that makes that 1 plus 1, which very simply is 2. Now in that denominator, again, just like the problem ahead of this is a difference of two squares multiplication. So the shortcut is first thing squared minus second thing squared. So this will end up being 1 minus sine squared of theta. We can keep simplifying this since 1 minus sine squared of theta, if you look at your formula chart, is the Pythagorean identity where that is equal to cosine squared of theta. And since cosine squared of theta in the denominator is just the reciprocal of secant, we can actually continue to use the reciprocal identity to change this into 2 secant squared of theta. So again, we found a common denominator, we simplified Pythagorean identity, reciprocal identity. So we're able to use these different identities from my formula chart to rewrite or verify different trigonometric expressions. The last example that's kind of the same is we're going to factor to simplify these trigonometric expressions. So it gave us a hint here of what to do. I notice in this equation that this top part is the difference of two squares again. So I have something squared minus something squared, which means immediately this is going to factor to 1 minus cosine of v, 1 plus cosine of v. My denominator, if I notice, both the first term and the second term after the plus sign have sine of v listed. So I can factor out sine of v, which means I'd have 1 plus cosine of v remaining. So again, this is the difference of two squares on the top, and this is a GCF on the bottom. I just divided out the sine of v. Sine of v divided by sine of v is 1. These sine of v's would cancel out. Now hopefully you notice that immediately I have a 1 plus cosine of v on the top and bottom. Since those are multiplied instead of added together, we can go ahead and cancel them so that I end up with 1 minus cosine of v over sine of v. Since I have a singleton in the denominator, I can split this at the plus sign. Again, this is only for singletons in the denominator, and basically give that denominator to both fractions. They have a common denominator. Now, 1 over sine of v, if you think about that reciprocal, is cosecant of v, and cosine over sine is cotangent of v. So we have simplified this trigonometric expression by factoring, splitting, and using the reciprocal and quotient identities. In example 5, it wants us to write one trigonometric function in terms of another. So it says, use a Pythagorean identity to write cosine of x in terms of tangent of x. So we're going to start with the tangent version of Pythagorean identity, which is 1 plus tangent squared of, we'll just use x, equal to secant squared of x. Now to write something in terms of something else, we want this function to say cosine equals to something where there's only tangents involved in the equation. So we need to figure out a way to get cosine to show up here. My spidey senses are saying that cosine and secant are reciprocals. So if I take the entire function and do the reciprocal of it, so reciprocal of the right side and reciprocal of the left side. So I have not changed the fact that this equation is equal to each other, because what I did on one side, I did to the other. I then can take that right side of the equation and say, well, that's just cosine squared of x. But I don't want this to be in terms of cosine squared of x. I want it to be equal to regular cosine, which means I just need to take the square root of both sides. So if I do the square root of 1 over 1 plus tangent squared of theta, x, that would be equal to cosine of x. Oops, I almost forgot my plus or minus. Please don't forget that. So we have cosine of x written in terms of tangent of x. I have cosine of x written in terms of tangent of x. Let's try one more. We're going to rewrite this expression 1 plus cotangent squared theta over 1 minus cosecant of theta in terms of sine and cosine, and then simplify the expression so that no quotients appear. So let's take that one that they gave us. This one involves a little bit more writing than normal. So 1 plus cotangent squared of theta over 1 minus cosecant squared of theta. It says first to write it in terms of sine and cosine. Let's go ahead and do that. So to write it in terms of sine and cosine first, I'm just going to use the quotient identity on the top, cosine squared of theta over sine squared of theta. And I'm going to use the reciprocal identity on the bottom, 1 over sine squared of theta. I have written it in terms of sine and cosine, check. But it goes on, it says, then simplify the expression so that no quotients appear. In fact, we're going to simplify this down to one trig function. To do this, my numerator and my denominator need to have one common denominator for both the top and the bottom. The common denominator in the numerator, weird sentence to say out loud, would be sine squared of theta. If you don't understand this step of the common denominators, because I'm not going to show my work in red, go back to example 2 so you can see that. This would end up being with the common denominator, sine squared of theta plus cosine squared of theta. This is because the 1 I had to multiply by sine squared of theta to have the common denominator. Cosine squared of theta doesn't get multiplied by anything because it has the correct denominator. The denominator of my denominator will also be sine squared of theta. When I force the denominator fractions to have a common denominator, I'd end up with sine squared of theta minus 1, because again, this 1 doesn't have the denominator I want, so I have to multiply by that, but this does, so I don't multiply. Now my spidey senses are looking at the numerator of the numerator here and saying, this is the regular Pythagorean identity, where that would be equal to 1. But my spidey senses are saying this is really close to the Pythagorean identity in the alternate form. We have written down that cosine of theta would be equal to 1 minus sine squared of theta. But we have sine squared of theta minus 1. So to get those two to switch, since subtraction is not commutative, meaning order matters with subtraction, if I make everything negative, so negative cosine squared of theta, the sine squared theta and the 1 can switch spots. So that numerator is a Pythagorean identity, but it is the negative version of it. So what I mean by that is, and I'm going to jump down here so I don't run out of space sideways, that the next step here would have the numerator of the numerator be 1 by Pythagorean identity. The numerator of the denominator is negative cosine squared of theta. And now I just have to remember my fraction rules. My fraction rules say you keep the numerator. You change the large fraction bar to a multiply, and you flip the denominator. And I just realized I have a typo. This should be sine squared of theta because that's what we wrote up here, and I just typoed that. But once I've done this, sine squared of theta and sine squared of theta will cancel out, which means that these two fractions, when I multiply them together, will just be 1 over negative cosine squared of theta. And I can simplify this one more step using the reciprocal identity. 1 over cosine is negative cosecant squared of theta. So if you notice, we started with this gnarly looking beginning of 1 plus cotangent squared theta over 1 minus cosecant squared of theta, and we ended up using a whole bunch of algebra and trig identities to get it down to this simple kind of problem. These fundamental identities that we've gone over in this part of the chapter will be vital to be able to do a lot of the problems that are coming up in the others. So make sure that you have a good sense of what those fundamental identities are, or just know to refer back to that front page of these notes so you have all of them ready for yourselves.